Hello everyone, I am an undergraduate from Tongji University, and today I am honored to share with you our work completed at Fudan University. It is UFO-3, Unsupervised Three-Compartment Learning for Fiber Orientation Distribution Estimation. Let's take a moment to dissect the smallest universe in the world, our brain. When you are listening to me, the sound waves are entering your ears and traveling through the auditory system. Auditory system is part of white matter in our brain. Thanks for white matter, different regions in our brain can talk to each other almost instantly. And these colorful colors represent white matter. We can visualize it in 3D using the technique called Xueqing. Xueqing helps us see the damage in our brain. On the left, it is a healthy brain and an injured brain. And it helps doctors to avoid critical white matter pathway when they are planning and operating. Going from diffusion NRI signal to Xueqing relies on estimating fiber ODF, which is short for Fiber Orientation Distribution Function. And that is our main focus. Let's zoom in on the fiber ODF image. It shows the directions in each voxel. And by connecting fiber ODF, we get Xueqing. Our goal is to estimate fiber ODF from diffusion NRI signal. By modeling the physicals, we get response function. Since response function is complex and unstable, the solution isn't unique, so it is a illustrates the inverse problem. Traditional methods are model-driven and usually relies on solvers to estimate fiber ODF. Once matter molecules hit cell membranes, its movements become anisotropic. Based on these assumptions, we can pre-compute response function and optimize the solution of fiber ODF. With deep learning, supervised methods can directly learn the mapping from input diffusion NRI signal to fiber ODF. It's learned from traditional method outputs, and it needs less input. Compared to traditional method, it is much faster. An unsupervised method estimates fiber ODF and reconstructs the diffusion NRI and matches it to the inputs. No ground truth needed. We proposed the UFO-3, an unsupervised method based on three-compartment model. It runs under half an hour, optimizes response function jointly, and better detects closing fibers. So what is three-compartment model? It models different signals as the sum of three components, F, alpha, and gamma. F reflects anisotropic water movements along axons, and it shows the directions in each voxel in our brain. And alpha reflects isotropic diffusion outside axons. Gamma models the trapped water. Each component is expressed in spherical harmonics. For metric Y and G, they use its physical price derived from diffusion theory of water molecule I mentioned earlier. So For UFO-3, we start with input diffusion analysis signal and project it into a dense spherical representation. And we apply a simplified version of UNet. We use pointwise convolution to avoid oversmoothing and save memory and time. The model directly gives three-compartment parameters and lambda is tropic. With lambda is tropic, we can get the response function and reconstruct the diffusion NRI. The loss has data consistency term and regularization term. The first term makes sure the reconstructed diffusion NRI close to the inputs, and the second enforces the three compartments parameters non-negative and sparsity. We run 3 main experiments, all using single-shell data, which has fewer measurements than full acquisition sequence. First, we test UFO-3 on 5 fiber setup, including single fiber and closing fiber in different angles. Even in tough cases like 16 degrees and 45 degrees, UFO-3 keeps the fiber shape sharp and gets the directions right, while others burn or mess up the orientations. Now let's look at the numbers. We use 2 metrics, mean angular error and angular correlation coefficient. UFO-3 keeps the error under 10 degrees and reaches 91% ACC, the highest among all methods. Even when there is strong noise, UFO-3 still gives accurate fiber directions. It is crucial for downstream tasks like trajectory and brain network analysis. Here is an in vivo example in the human brain, taken from a region where 2 major fiber bundles, the corpus callosum and the superior longitudinal fasciculus. As the white arrow shows, there is a sharp turn in this area and most existing methods struggle to capture it here. Still, UFO-3 clearly separates the closing fibers. Its results are consistent with high-quality multi-tissue references. It is multi-tissue CSD and tranche that is 3-compartment model. In comparison, other methods either blend the orientation or produce extra incorrect peaks. Figure 3b shows the estimation of extra exons diffusivity. Low values in white matter, high values in CSF, and intermediate values in gray matter and complex fiber regions. This matches well with the different regions shown in the reference. This anatomically plausible pattern proves the optimization of response function is interpretable and reliable. Here is Figure 4. It shows the trajectory of the breathing project system using different methods. It is a tough job, especially when it comes to complex fiber shapes. UFO-3 is sensitive to complex fiber shapes like sharp turns and closing angles, and other methods tend to miss the details. To wrap up, we present UFO-3, a biophysical and unsupervised method to estimate fiber ODF. It works with just single-shot data. That means limited inputs, but still gives faster results. Gently optimize the response function and fiber ODF. Next, we plan to test it on larger datasets and make it even faster. Finally, I'd like to thank my amazing courses, as well as the Chinese Human Connectome Project and ISNIM 2015 Tractometer Challenge for data providing. I am currently looking for a PhD position, and if you are interested in my work or want to collaborate, feel free to scan my QR code here to check out my homepage or stop by my poster booth to chat more. Thanks so much for listening. I'd be happy to take any questions.